Okay, so it says it is live, and I eventually trim the beginnings off of all of these
Okay.
while I do the sanity check of, are we all here? Is it working? Okay, so I see it started on YouTube. Okay, so I'm ready to go if you are.
All right, sounds good.
Okay. Hello, everyone, and welcome to what is now the 9th episode of the Center for Lunar Science and Exploration Hangout series. Tonight, I'm afraid to say that I'm missing my co-host, Andy Shaner, who is out with a minor medical issue. We wish him speedy recovery and hope that he is back with us next month in December. I do, however, have a fabulous guest with me tonight. Addie Dove is here to talk to me about her work down in Florida at the class node for the SSERVI, space exploration program. Welcome, and can you give everyone a little bit of an overview of what it is that you do?
Thanks. Yeah, so I am here at the University of Central Florida, UCF in Orlando. And this is where we have the sort of home base of the CLASS node. So CLASS is the Center for Lunar and Asteroid Surface Science. So like you said, it's one of the SSERVI nodes. And our focus here is really that sort of fulfilling that motto of science benefits exploration and exploration benefits science. So we really try to work at the intersection of those two areas. And the areas we really focus on here are the planetary surfaces. So places like asteroids, the moon, and the moons of Mars all have interesting dust-covered planetary surfaces. And that's really what we focus on here.
And looking over the types of things that are happening down with your group, it really involves dust in its many forms and how that dust gets stirred up.
Mm-hmm.
A lot of times we think of like moon dust and the broken up surface of the moon and how it got into everything the Apollo astronauts had.
Mm-hmm. Yeah.
But the science gets weird in low gravity, doesn't it?
It does, yeah. So on the moon, the gravity was lower than it is here on the Earth. And the astronauts sort of, when they ran around, noticed dust clouds get kicked up a little bit more easily than here on Earth. And they had some problems with the wheels of the rovers storing up more dust than they expected. But it turns out when you go to places like asteroids or small moons, the gravity there is even lower. And so you do get these really crazy environments where you have different gravitational potential based on the shape of the body and how it rotates, and also really interesting dynamic environments that have to do with micrometeorites hitting the surface and also electric fields and solar wind interactions changing the dust motion on the surface.
So that's a whole lot of different ideas. So
Yeah.
let's try and unpack a little bit of this. So
Okay.
so for instance, when you start talking about low gravity,
Mm-hmm.
what my understanding is on a standard asteroid that isn't one of these like 1,000 kilometer across, but a more couple 100 kilometer across,
Yeah.
someone like you or I, we'd feel like we weigh as much as a piece of paper.
Yeah, so it's sort of that weightless environment you think of. It's the gravity is so negligible there that it's going to be sort of what we think of as weightless. So it's actually sort of analogous to what the astronauts feel on the International Space Station. It turns out the gravity levels on the ISS are very similar to gravity levels on these small asteroids. So it's like 10 to the minus 6 times Earth's gravity, for instance.
Or put another way, you take too strong a step and you're off and flying
Exactly.
away.
Yeah. Yeah. You don't want to jump off the surface of an asteroid because you might not come back down.
It's literally jumping off.
Yes, yes. Yeah, and this is actually a big problem for exploration because there's not really a great way to land on the surface of an asteroid. You can sort of plop down and hope when you bounce, kind of like Philae, right? You hope you bounce back down, but it's really hard to grapple on to that surface.
And that was in fact the problem with Philae is Philae had its harpoons and
Mm-hmm.
failed to deploy them.
Yep.
And as we look towards Bennu and OSIRIS-REx in the future,
Yeah.
this is basically a fly by, grab a rock and keep going kind of a mission.
Yeah, exactly. Yeah. So Bennu is an asteroid that has an interesting shape, and OSIRIS-REx is going to just sort of touch down on the surface. It's called tag SAM because it's that sort of it's tagging and going, right? But it's got a little sample mechanism, so it's just going to sort of scoop up some on the surface and leave.
And what's fabulous is I've seen team members, instead of doing a fist bump, they do
Mhm.
a tag and grab, and so this is how
Excellent.
they're trying to communicate it out to people, and it's fully
It's like
giggle
it's a
worthy.
nice geeky secret handshake.
Exactly. Exactly. Let's do the fillet bump, not fillet, the Bennu bump, I guess.
Yeah, there you go. I like it.
Now,
Feeler bump would be a couple of bounces, I guess.
it's true.
And then
And
you
then
go
you,
hide.
yeah. Yeah, it's that and then you die that's the problem.
Yeah, yeah.
Now, with these low gravity environments, one of the things that you guys look at is impact ejecta.
Hmm.
And you get impact ejecta from rock from space, whether it be a giant asteroid, smaller meteoroid, hits other rock in space, whether it be a big asteroid or a bigger moon,
Hmm.
and splatters debris around. Now,
Yep.
with such a low gravity environment, how small can you get and you still have ejecta?
So basically as small as you can think of. So these little tiny centimeter, millimeter sized particles that can hit the surface, we call them micrometeorites, they can cause ejecta on the surface. So usually when we think of impacts, right, we think of big, giant, high energy, large rock impacts hitting the moon or hitting the earth and causing huge amounts of ejecta. But you can actually have just these, at such low gravity, these little tiny things hit the surface and cause a ton of ejecta also. We do a lot of experiments here in sort of simulated microgravity environments, so in things like drop towers or on the Vomit Comet or on the space station. And that we do those because you get microgravity environments and you can see how you can get these huge amounts of ejecta even with little tiny low energy impacts.
That is completely wild and probably leads to all sorts of crazy physics when you're dealing with your own stomach as well as your projectiles on the Vomit Comet.
Indeed, you hope the projectiles are just in the experiment.
Exactly.
So,
Exactly.
and usually they are.
So I can see that we have a bunch of audience members out there. Thank you so much for joining us this evening. If you have any questions, I'm watching the chat on YouTube, and I'm happy to bring any of your questions into tonight's discussion. So with the work that you're doing, you're looking at a whole lot of different worlds, trying to build up an understanding of our solar system. And what what is the story that you're looking to tell across your various experiments?
So we're really looking to understand both how asteroids and moons and things like that form and evolve, but then also what happens when you're interacting with them. So if we want to explore these things, how are we going to interact with them? And what happens when we touch down on the surface, for instance? What happens to that interaction, and what do we learn right when we're there?
And where you're seeing small granules create large ejecta, the idea of trying to land a fairly large spacecraft must
Yeah.
be somewhat daunting. What are some of the things that you're finding that future spacecraft are going to have to be aware of?
Yeah, so the challenges are really not only figuring out how to interact in such a low gravity environment and really sort of dock with an asteroid as so much as land on it, um, but also if you have anything like a jet with your spacecraft, if it's landing, if that jet is hitting down into the soil, how is it going to kick up the regolith, the dust, and maybe block what you're seeing on the surface or come up and actually hit your spacecraft, for instance? What kind of damage can that create? Um,
And this goes back to the electric fields that you mentioned earlier, because one of the other horrific properties of dust is when the dust rubs against each other,
yep.
it transfers charge. This is
Hmm.
actually part of how lightning occurs. Is it's not just dust, but it's water particles frictionally interacting in our atmosphere. You end up with charge distribution across your cloud of dust.
Yep.
And does this support the dust? Do you end up with like electrically charged, internally supported clouds of static hell?
That's a very good question that we don't know the answer to, basically. So there's a lot of studies that are related to sort of dusty plasma. So what happens when you have dust forming this cloud, or even just dust in sort of an electric field moving around? Because like you said, it gets very charged up due to a number of mechanisms, and it's going to get worse if we sort of put a plume of gas down onto the surface and mix it up even more. So we're doing a lot of experiments to understand some of those things.
And this leads to all sorts of, well, NASA has vast programs dedicated to dust mitigation.
Sort of, yeah. There was a good lunar dust mitigation program that was established when we sort of were planning to go to the moon. And since then, there's different groups working on studying some of the charged dust properties and how you can get rid of dust if it's on surfaces with additional electric fields or with brushes or magnetic wands. Different interesting ideas for ways to pull dust off of surfaces.
One of my favorite ones so far is there was a group in, I believe, Tennessee, who found that if you heat is sort of the right word. If you radiate lunar dust with the right microwave
Mhm.
radiation, it will melt. And so you can essentially have a slow moving crawler vehicle with microwave radiators on the bottom of it that essentially build roads by.
Yeah. Yeah, one of the really interesting things, and this is actually one of the areas we work on with different groups at Kennedy Space Center and other groups here, is understanding how you can use the fact that there's all this dust on surfaces to your advantage. So it's called in situ resource utilization. ISRU is the short form of it. But so one way is to make roads just by melting the dust, but you can also process the dust by melting it and maybe pull water out of it and use that for fuel or for resources on a surface. And there's also a lot of interest in like asteroid mining. So what other elements and metals and minerals can you pull out of asteroids?
And this gets back to the idea that dust in space is radically different from the dust we have here on Earth. Here in my office, I have a constant layer of dust. I live in a very old house, so there's a constant fine grain of ancient plaster falling from the ceiling.
Hmm.
There is most dust on your typical household surface is actually like bits of human.
Yeah.
So debris from dry skin, from the dog's dead skin, particulates of food. Basically, it's organic stuff and stuff falling out of the ceiling. In space, none of that's the problem. What you're dealing with instead is silicas, is large complex molecules. So it's either things that have been broken down or built up slowly over time. And this is not the fine, gentle, just annoying dust we have here on Earth. What are some of the physical properties with the dust in space? Oh, your feed seems to have frozen. Okay, now you're back. Can you hear me okay?
Yeah, sorry about that.
It's all right.
Can you see me?
Yeah. So what I was asking is, what are some of the physical properties of this very different silica and complex molecule dust that we have in space?
Yeah. So as you were saying, most of the stuff here we have on Earth is these organic materials, but these dust grains are insulators, and so they can have weird charges on them. And like you said, that's how they get tribocharged. They get charged up by rubbing together. They also can have little.
Hello? I'm sorry for the technical difficulties. Sometimes our video does not stay as secure as one might wish, and it looks like Addie is having some technical difficulties on her end. There, you're
Yeah, sorry
back
about that.
again. It's
I'm
okay.
back. Okay.
Okay, one more try.
So, Okay, so yeah, so these silicate grains behave a lot like the organic grains you see like clinging to your TV. So in these low gravity environments, they're going to have little electrostatic sticking forces that are going to stick them to things, just like that dust grains that stick on your computer screen or your TV or whatever.
Now, they do have the disadvantage where if I get a little bit of dry skin in my shoe, it's not going to bother my foot.
Yes.
But if I got some lunar dust in my shoe, it would shred my foot.
Yeah, so the dust grains that we think of them, usually when you think of a dust grain, you think of a nice fluffy particle. But dust on the moon and asteroids is actually really jagged particles that are made up of this constant bombardment from rocks, just breaking other rocks apart. And so you just get these really jagged, nasty particles. That don't get rounded or anything like that because there's no erosion and weathering like there is here on Earth for sand grains, for instance. So these really jagged particles were what caused a lot of problems with the Apollo astronauts. They stuck in their spacesuits. And they also, when inhaled, can have different properties, can cause respiratory problems.
And one of the new areas of research that is literally just starting is how nanoparticles, and this is just another kind of nanoparticle that's
Mm-hmm.
naturally created rather than laboratory created.
Mm-hmm.
How do nanoparticles interact with biological systems like you and I?
Yeah, yeah, exactly. What happens when you breathe them in or you swallow them, for instance? These really fine particles like to get into different parts of your respiratory tract, for instance, and can cause big problems.
So here you are in Florida doing research on what happens with collisions on small bodies,
Mhm.
potentially worried about what will happen to our body with explorers someday in the future. It's
Yeah,
pretty cool.
it's a fun adventure, and it's interesting to study how the different chemical makeup of asteroids is going to affect what the regolith, what those dust grains are made out of, because lots of asteroids have different composition. Some have a lot of carbon, and some have a lot of organics, and some seem to be a lot of metal. So if we visit any of those, they're going to behave. They're going to have very different compositional properties.
And then there's always the challenge of we hope that these very these bodies that haven't undergone a lot of chemical weathering, like we have on the surface of the Earth, the surface of
Mhm.
Mars, they will have trapped inside of them bits of the origin of our solar system that when you release gases locked up in the minerals, you get the chance to sample our early solar system. How do you approach trying to figure out how do we get these samples with a spacecraft someday in the future?
Yeah, so that's one of the challenges for OSIRIS-REx and going to Bennu is trying to get that sample and bring it back. One of the really and right now the idea is to have a sample return where we actually bring it back to Earth because most of the techniques we have to study something like that we have here on Earth, and we haven't really figured out ways to take them to other planets. We have all these really fancy big lasers and microscopes and things like that here that we can do here on Earth, but it's hard to make them small enough to send to a spacecraft to go to a planet. So one of the challenges is advancing that technology to be able to send X-ray spectroscopy, things like that, to an asteroid and really understand the surface properties there in place.
And it's it's fascinating to me the way we can look at how things work on such a wide variety of bodies, ranging from moon kind of top of the scale down through Ceres, Vesta, Bennu, to
Mm-hmm.
these smaller and smaller rocks that then have rocks on top of them and are getting bombarded by smaller rocks, and it's rocks
Yep.
all the way down.
Yeah. And literally, some of them we think aren't even one solid body. So a lot of these really small asteroids seem to be what are called rubble piles. So they're basically not a solid rock. They're a sort of a loosely bound cohesion of smaller rocks. So we call them rubble pile asteroids because it seems like it's just a pile of rubble that's sort of gravitationally bound together, but not really stable. So what happens when we interact with one of those, for instance? Might not go so well.
No, no, there are, especially when you start thinking about that whole microgravity environment of
Mm-hmm.
we weigh like a piece of paper.
Yeah, you
Um,
weigh a piece of paper, it might be really easy to disturb that surface.
And these are the kinds of things that make science so amazing today is we are at the point of just starting to understand this. So there's still so many questions to answer,
Hmm.
but we're at the point technologically of being able to go out and grab a rock and bring it home.
Yeah, exactly. So it's already been done. We've had a couple of sample return missions so far. So we went to Itokawa with an asteroid, and we're trying to get more sample return missions to actually be able to study these things. And we do have that technology now, so it's pretty exciting.
And what's cool about these new sample return missions is we've always had samples from outer space. We call them meteorites and they fall out of the sky and occasionally destroy things.
Yeah,
But we don't know exactly where these samples came from. So we
exactly.
have rocks from Mars, but just like one part of Earth is different from another part of Earth, we want to know where those Mars rocks came from so we know what each part of Mars is.
Yeah, and most of the meteorites we find are from some other body somewhere in space, right? So some of the meteorites we find here on Earth, we can sort of group together and say they're very similar. And there are a few that we think we identify what family, what asteroid family, for instance, they're from. But it's really hard to tell where it came from and also what it's been through since it left its sort of parent body, right? So
Right.
it's traveled through space for probably a really long time, thousands, millions of years. And then at some point it came through our atmosphere. And then maybe it was buried in Antarctica for 10,000 years. So there's a lot that's happened to our ground samples that's changed them. But so we have to really understand a lot about them to know where they came from.
So, what are the questions you're most looking forward to trying to answer in the coming years?
So my biggest questions have to do with how does that dust move around on the surface? So I really want to understand what those environments are like and really what sizes the dust grains are, for instance, because that's going to tell us a lot about how they get charged and how they can move around. When you hit a surface, for instance, you expect a lot of the dust to come up, but you can imagine different particles will have different speeds and they might fall back to the surface, and then some of the smaller particles might get kicked off the surface. And so you might have different size distributions of those dust grains based on the type of body and what it's undergone. So really understanding these dusty surfaces and what they're really made up of is this big question that we're sort of getting closer and closer to answering.
Now to just take things someplace a little bit less serious for a moment. And
Okay.
what's cool is this is the kind of science that you can just giggle while you discuss. Now, you have to explain to people that you have a PhD for studying dust.
I do, yeah.
How did you pick dust? And how do you explain this to other people so that they don't giggle for the wrong reasons?
Well, usually I say I study dust and let them giggle a little bit anyway. I also study dust in vacuums, so that helps eliminate the giggles. No,
That's just punny.
I exactly right. Yeah, so I usually put dust in vacuum chambers to do laboratory studies, so it doesn't help the giggle factor. So I think one of the nice things about studying dust is that it's actually sort of relatable. When you say that, people do giggle, but then they're like, "Oh, but." If you explain how it's different but the same, it really sort of ties in, and then everybody offers to help have you come over and clean their house also. So
Yeah, it I can see all sorts of strange conversations when you get introduced to new people. Um,
yeah, yeah, I have my PhD in studying space dust, so it's it gets some interesting conversations. It's also like a lot of astronomers hate space dust, right? Because it interferes with observations. So there's different types of space dust. So you have to clarify. I just study the stuff on surfaces, not the
right.
stuff that's blocking your observations.
And the for those who don't know, when you see a super red sunset, that's because there's a lot of fancy word is aerosols and particulate matter. Unfancy word is dust and
Yep.
gook in
Yep.
the atmosphere. And so the dust you study, when it gets between a telescope and the sky, reddens the light that's able to get through by scattering out all of the blue light.
Hmm.
And so people like me get irritated at the dust.
Yeah, dust in space.
Exactly.
But it
Exactly.
sounds pretty cool when you say it that way. At least I tell myself that. I don't know.
Now, you did have to get inspired about dust. And what
Mhm.
was it that inspired you about it to want to spend your life studying?
I've always been interested in space exploration. I would love to go to the moon and actually study it, or just walk around on the surface, but I'll also do some science. Um, but so I've always been interested in that, and I got involved in a project. There's this big question from the Apollo days of how the dust moves around, and some of the observations we see are very intriguing for where we see dust on the surface. So it sort of naturally tied into my interest in exploration and understanding these environments. So it was sort of a natural fit for me, I think.
That is cool. Now, you had to get in love with space to begin with, and I
Yep.
know one of the questions that our audience asks all of us most often is, what caused you to choose science as a career to begin with?
I think it's been space all along. So I've always just been interested in looking up at the stars and in the space program. I went to space camp when I was a kid, so that helped me on my path. I know it's great. I worked there when I was a little bit older. And so it's always been a fascination of mine, just space exploration. Um, and so I knew I wanted to study science because I liked doing sort of math. I didn't love physics sometimes when I was younger, but I liked the challenge of it, I guess. And so, sort of those challenges and answering these big questions about the universe and exploration is sort of what drives me and inspired me as a kid, too.
And you're now down on, well, not you're not on the Space Coast, but you're pretty darn close to the Space Coast. So
Yep. Yeah,
you're
we get to see launches all the time. We can watch them from my backyard. So
that is kind of awesome.
it's pretty great. It's a good perk.
So so you're part of a survey node, you're
Hmm.
working and studying dust on a variety of different surfaces. You're clearly looking forward to OSIRIS-REx getting to Bennu.
Yes.
If you were mentoring a child like you, what would you tell them that when they're grown up like you that they should be looking forward to?
Um, well, a child these days will probably be looking forward to doing science on Mars, I believe. So I think at that point we will actually be doing science on the Mars, hopefully on the moon again, actually. So I think looking at the future of how we study things in place and how we use exploration and science together will be a really big factor.
And if I'm hearing you correctly, you would happily take that today's child when they're an early researcher to the moon or Mars or anywhere in between to do their science.
Definitely, definitely. As long as I could come back, but
Okay, fair
I would
enough.
definitely go. Yes, happily.
That is really awesome. Now we're starting to run out of time. Where can people go and learn more about the things that you and your team down there in Florida are doing?
So class has a website. If you Google UCF class or Center for Lunar Science, sort of any of those combination of words, you can find it. We also have a Center for Microgravity Research that we do a lot of our low gravity experiments in. We have a YouTube page, so it's UCF Microgravity, and we have a website, and so you can find a lot of those resources there. And I'm on Twitter. I'm Astro Addy, and we have a number of other resources there too as well.
That all sounds great, and this has been a fully giggle worthy episode because, well, just dust and
Yeah,
the static problems that it creates, and
yeah.
it's small and evil and does cool things.
You're exactly. It's going to be a big challenge, but it's also really awesome and interesting and can tell us a lot.
So this has been a great and quickly flying 30 minutes. Thank you so much for joining us this month. And For those of you out there watching, go back to our YouTube channel, check out the other 8 episodes in our archive, and subscribe. We have a new episode coming out roughly once a month. We aim for the 3rd Wednesday of the month. Now that we're hitting holiday season, things tend to get a little bit more chaotic, but you'll never miss an episode if you hit subscribe, because YouTube likes to send notifications. So follow us, watch the shows in our archive, and learn about this universe that we share and this solar system that we're on the cusp of beginning to explore again with new manned exploration and womaned exploration.
Yes.
And let's get the human beings off this world and exploring others and doing science.
Indeed.
Thank you so much for joining me, Addie. It's
Thanks for
really been a
having me.
pleasure.
Thanks for having me.